Hello everyone and welcome to my YouTube channel. Today we are tackling one of the most powerful tools in linear algebra, the singular value decomposition or SVD. If you have ever wondered how Google compresses images or how Netflix recommends movies, SVD is the secret sauce behind it. Well, that we will discuss in some another video. Mathematically, we are breaking down any matrix A, be it square or rectangular, non-diagonalizable, into three special parts as A is equal to U times sigma times V transpose. Let us talk about these decomposition factors. The matrix U is known as the left singular matrix and its columns are orthonormal vectors. The matrix sigma is the matrix of ordered singular values and is a diagonal matrix, while the matrix V transpose is the right singular matrix whose rows are orthonormal eigenvectors. Here is a challenge. Find the singular value decomposition of the matrix A 2, 2, negative 1, negative 1. To make sure we don't make any calculation mistakes, we will follow the 7-step master plan. Step 1. Calculate A transpose A. Step 2. Find eigenvalues of A transpose A. Step 3. Construct the singular matrix sigma. Step 4. Find the orthonormal eigenvectors of A transpose A. Step 5. Construct V transpose, the right singular matrix. Step 6. Construct U, the left singular matrix. And finally, step 7. The final SVD. We begin our calculations by finding A transpose A, which is the product of A transpose taken with A. In this case, we are going to get the matrix 5, 3, 3, 5. Moving on to step 2, where we determine the eigenvalues using the characteristic equation. Note that the matrix A transpose A is a 2 by 2 matrix, so you can definitely go ahead and use the shortcut method. With the trace of 10 and determinant of 16, we get the characteristic equation as lambda square minus 10 times lambda plus 16 is equal to 0. On solving this quadratic characteristic equation, we get lambda 1 is 8 and lambda 2 is 2. Do not forget to write these eigenvalues in descending order. It is an important part of SVD. Step 3. Once you have the eigenvalues of A transpose A, we can now determine the singular values sigma 1 and sigma 2 using the relation sigma I is equal to positive square root of lambda I. In this case, we get sigma 1 is equal to 2 root 2 and sigma 2 is equal to root 2. We are now ready to write the singular matrix sigma, which is a diagonal matrix of the singular values we have obtained. Said that sigma will have 2 root 2 and root 2 on its diagonal, and other non-diagonal entries are all 0. Thus, we have one of the decomposition factors ready with us. Next, we find the normalized eigenvectors for A transpose A, giving us a right singular matrix V transpose. For that, we start with the matrix equation A transpose A minus lambda I times x is equal to the 0 matrix, and we will determine the eigenvectors for both the eigenvalues 8 and 2. For lambda 1 is equal to 8, on performing the elementary row operations or EROs, we get V1 minus V2 is equal to 0, which gives us that the eigenvector V1 corresponding to the eigenvalue lambda 1 equal to 8 is column 1, 1. Recall step 4, orthonormal eigenvectors. So next we find the magnitude of V1, which is square root of 2, and divide V1 by it to get V1 hat. Likewise, for lambda 2, the normalized eigenvector will be 1 over root 2, negative 1 over root 2. With these two normalized eigenvectors, we construct the right singular matrix V transpose. Prior, the matrix V has V1 hat and V2 hat as its column, and next we take its transpose. And there we are, the right singular matrix is ready. Observe that V is an orthogonal matrix of normalized eigenvectors, and that's why we call it as orthonormal. On to the second last step, construction of the left singular matrix V. We use this formula to find Ui, which are columns of the left singular matrix. Using it, we get U1 as 1, 0, which is a normal vector since its magnitude is 1. Similarly, solving for U2 gives us 0, negative 1, another normal vector. And note that U1 and U2 are orthogonal. And so we have the right singular matrix ready, 1, 0, 0, negative 1. Now, putting all together, we write the singular value decomposition of A. We had A is equal to U times sigma times V transpose, which gives us this. Leaving it to you to multiply and verify the answer. Now it's your turn. Try finding the singular value decomposition for A 1212 and comment your answer below. If this helped, like, subscribe and share. Thank you so much for watching till the end and happy learning.